is Victor Moll, one of the greatest experimental mathematicians alive today, and hence of all time, who will speak about valuations of classical sequences, examples in search of a theory.
Thanks.
We will be taking Victor out for dinner as usual place. If you'd like to join us, please let me know immediately after the talk.
Okay, thanks for the invitation. I heard that they're filming the talks now, so I'm going to make an effort that has never worked in about 30 years, is I'm going to try to speak slowly. I saw a video of a talk of mine a long time ago. I could not believe how fast I talk. So this is joint work that I've been doing for a while with several, so there are lots of Rutgers connections. So Luis Medina was my student, and a postdoc with Tulane, and Teddy belongs to Tulane now, and me, and Shinju is also connected to this problem. So I apologize for those of you who have heard part of these things before. This is for students and students only. So I'm going to try to keep it as slow as I can. So the message that you will receive is the following, that many times you get sequences that will appear in somebody else's work. And if you decide to become interested in the number theoretical properties of that sequence, even though the sequence itself doesn't come from number theory, if you decide to study prime factorization or other issues of that sequence, you will get a rich collection of problems that will keep you entertained for a while. So at the beginning, I will just talk about notation. So if you have an integer n and a prime p, and you factor in this form, p to an exponent times a number not divisible by p, then the exponent is the quantity that we're interested in, and is denoted by nu sub p of n. And I call this the p-adic valuation of n. So whenever you hear me say the p-adic valuation of something, it simply means the exponent of p that appears in that in the factorization of that number. So for example, if you look at a random number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, that's the factorization. And so, for example, the power of 2 that divides is 1 because it's just as 1 that appears here. So nu of 3 is 2. It's obviously a typo already. There's an n missing in there, but that's the way typing goes. Okay. So the message that I said before, and what I want to concentrate in this talk, is that given a sequence of integers and a prime p, I'm interested in this object, this new sequence. Okay. There'll be lots of pictures. So my message is, the kind of things that I like to do is you compute in any language of your liking. Mine is Mathematica, I'm sorry to say, but that's the one that I learned first. And so the mother tongue is hard to ignore. So you do some runs, you compute, and you generate a picture. And what I try to do is, I essentially at heart am an analyst, I think. So what I like to do is I like to have a formula that reflects the picture. So here's an example, the simplest example of all. So the graph that you see here is the power of 2 that divides n. So starts at 1 is 0, at 2 is 1, at 3 is 0, at 4 is 2, and so on. So once you see this graph, now you can start asking all sorts of interesting questions. So for example, clearly there's lots of symmetry in this picture. And interesting here is that there is a folding mechanism, right, that is easy to see. So for example, you can determine that once you get to this point here, there's sort of an end of a cycle of this 3-piece here. And if you want to generate the next part of the picture, what you do is you look to your past. You see what's the highest value you have is 2. You add 1 to create the next spike. There's your next spike. And then you reflect this whole piece of the graph here to generate the new part of the graph. So this is sort of a folding mechanism that you can hopefully try to explain, and it's an easy proof that I like to see pictures, generate properties, and then try to prove them somehow. Most of the time I can't, so that's what I'm talking here about. Here's the p-adic valuation of n factorial. So this is the first picture. I should have put these two pictures separately, but to save time, put it in one. Here's what you get if you compute the p-adic valuation of n factorial. So it's the power of 2 that divides n factorial. And obviously, when you look at this picture, something immediately comes to mind is that this is a line, more or less, right? So clearly, there's an asymptotic behavior of this picture. And if you look at the data, look at the scales here, this is the line y equal x. And then you subtract from this picture, you subtract this asymptotic behavior, and you get a picture that has interesting patterns. Here's the error, what I call the error term, or deviation from asymptotics. So this is what you get. And one more time, you see patterns that repeat. So for example, that picture here gets sort of shifted up here. And then you can understand, for example, one question is, how do I shift? What determines the shift? The kind of things that you look in pictures to understand the behavior of a function is, okay, let's look at the minima. Sometimes this piece is 0. Where are the minima? What is the location? You can generate a table of this data to look at the minima, and then you say, okay, can I figure out where they are? And from that, you can build on to this and to completely understand this error term. That can be done in some simple examples, but in general, one can't. So here's a formula that you learn in most basic, the first course in discrete math, or the first course in number theory. It's a formula of Legendre that says that in order to compute the p-adic valuation of n factorial, so the power of p that divides n factorial, you have a series that is actually a finite sum. But what you do essentially is you divide, so for example, for k equal 1, you divide n by p, take the floor of that. That essentially you're picking every pth term that gives you all the multiples of p. But then when you take those out, you're left with some other part, namely the numbers that divisible p squared. And so you can take them all one at a time, and you get this series. There's a second form of this theorem that is actually more useful for the kind of things that I like to do. Oh, here's an example. So the number, it's good to give examples. The number 581 factorial, when you compute the p-adic valuation, is 143, because this sum, as I told you before, reduces to only 3 terms. After the next one is 625, so the fourth is 0. And there they are, is 143. And this kind of question appear in elementary math books, right? Or the question is typically asked is, how many zeros are at the end of 581 factorial? And you can check if you do it by hand, there are 143 zeros at the end. Okay, I killed it. Oh, here it is. Here's the form of this theorem of Legendre that I like to see. I think this formula deserves to be as popular as the one with the series because it's more useful. What you do is that you take your number n and you write it in base p. These are the digits base p. I'm going to do with my, okay, I have a better one. So you write the number in digits base p, and then you sum the digits, and the formula for n factorial is more compact, like that. So you see, these are the kind of things that I'm looking for. N factorial, okay, I grant you, is an easy function to understand. And so what I would like to know is that if I have a more complicated sequence that looks more complicated than n factorial, I would like a formula like this, something of that nature, some kind of analytic expression. Well, sometimes you have to admit more functions to your language. So here, the sum of digits is one of the basic functions that appears. Here's an example. I'll skip it. You get 143 again, by the way, if you check. So how does one go ahead and start by thinking, what do factorials satisfy that can be generalized in an interesting way? So factorials satisfy this is an. This is an minus 1. So factorials, a is equal to t. Factorials satisfy recurrence of this type, they're called recurrence as recurrence of first order, with some polynomial as the coefficient. So that should be the natural generalization of what things are for factorials. And we have a theorem, this is joint work with the people that I mentioned at the beginning, that if you have q is a polynomial with integer coefficients, and then what you need to do is you need to factor this polynomial q in the p-adics. These are zp are the p-adic integers. So p is the prime that you're interested in looking at the congruence. You see how many roots your polynomial has in zp. It factors like that, and then there's a piece that is not factorable. So not factorable in the p-adics simply means that the congruent q1x congruent to 0 mod p cannot be solved. Right? So factoring the p-adic is the same thing as solving recurrences. And then there's we prove a formula for the p-adic valuation of the sequence that has a linear growth. N is here the variable. N over p minus 1, if you remember, is the formula for the factorials. So it's a formula very similar to the p-adic valuation of factorials. There's a coefficient that is determined by the number of roots, and then an error term. We have a semi-explicit form of this error term that is similar in terms of this digit counting function, but it's not very pretty, so I'll just skip it. If the polynomial doesn't factor, then it's slightly more complicated, but a formula of a similar type. So if the polynomial is irreducible, it's an easy exercise to actually check that being irreducible is the same thing as saying this number is finite. There's some kind of compactness argument, but that's not so important. So you define that the number is the largest power that divides any number of the form q of I, and you take m to be the degree, there's going to be some expression that will be linear growth in n plus another term, or some error term here. So this formula indicates that your polynomial has no roots in the p-adic, can also be done. The formula is slightly more complicated, but the phenomenon is the same. Okay, some examples. So this is not very experimental. How we got the theorem is experimental. We got lots of data. We saw that sometimes the slope was the right one, sometimes the slope was not the correct one, and we didn't know what was going on. And then we factored the polynomials, and then we realized that was it. Here's a well-known material, right? You take your favorite numbers, the central binomial coefficients, and if you look at the p-adic valuation of the central binomial coefficients, it can be expressed in terms of this digit counting function. In particular, the p-adic valuation of central binomial coefficient is exactly the number of ones that n has in the binary expansion. In particular, that proves in one line gives you a proof that this number is always even, because n must have at least one binary digit, and half of the central binomial coefficient is odd if and only if there's exactly one 1 in n, and therefore n has to be a power of 2. That's the shortest proof that I know. I mentioned the central binomial coefficients because I want to show you how we find formulas. Okay, here's a picture.
So it's a special case of the famous fact mod 2. Pascal mod 2.
Yeah. Yeah. So here's a picture that you get when you look outside. I gave you formulas for the p-adic valuation of central binomial coefficient. How about 3-adic? Take the central binomial coefficient and look at mod 3. So that's the picture that you get. So my task now is to figure out a formula for this graph. That's what I like to do. You look at this picture, and then some days when I'm very optimistic, I say I'm going to find a formula. Some days when I'm not, it's sort of hopeless. But what I want to do is to get a formula for this picture. So this is what the picture looks like. 1,000, n is equal to 1,000 here. So there are all sorts of patterns, right? There are all sorts of repetition patterns and things like that. And I want to try to explain to you how we arrive to a formula from these pictures. Here's the data. Okay? So the data is, what you see here is a list of these numbers. The power of 3 that divides central binomial coefficient. Now hopefully you will see the difference in the next one. More data, but now there's some numbers in bold that I should have put them in red maybe. So this, can you see the difference or no? My eyes are too old. So there's a 0, 1, 0 is in bold. There's a 0, 1, 0 again. There's a 1 to 1 that is really a 0, 1, 0 shifted. So we look at this data. So I spend most of my day looking at data and staring at it to figure out something. And once you see some patterns, for example, you see this 2, 3, 2 appearing here. Right? Here's another 0, 1, 0. So that gives us the following idea. What I'm going to do is I'm going to take this data and I'm going to compare it with the data obtained by taking the sequence 0, 1, 0 and repeat it with period 3. Okay? So I'm going to take this 0, 1, 0. I want to eliminate this first pattern here. So I don't want to make too much damage, so what I'm going to do is I'm going to take this 0, 1, 0 and repeat it modulo 3 and subtract and hope for the best. Right? So this is what I compute. The power of 3 that divides central binomial minus 0, 1, 0 extended periodically with period 3. So this is the first one. This is the power of 3 divides 2 and choose n. This is the 1 minus the pieces subtracted. So they look more or less the same to me. Here's 2 refinements. That's the original picture. That's the peaks 0, 1, 0 modulo 3. Then you look at this difference, you stare at it again, and you find another pattern, and you subtract. Right? And then you might have to scale the pattern a little bit to adjust things. This is purely empirical. Or experimental, as they say, some people. Right? So you see that there's a refinement. At the end, the picture is getting more and more, giving more and more hope that I can understand this because I can see the patterns here. It's hard to see the patterns here, there's too much noise. So I can look at them here, and I see that this piece goes up, and it repeats here, and so on. So I can start playing my game to see what the structure of the problem is. Okay, let me show you now the analytic version of what you just saw. Before I showed you data with a picture, and I take some subsequences out of the picture in order to get something simple. And I want you to think about this old problem in a different way now. So you take your number n factorial, divided by n minus 1 factorial. That's a recurrence that should be there. And here's the theorem again. Right? This is Legendre's theorem, first version. So you take the power of p that divides n. The first term gives you this number here, the power of n, p that divides n factorial. The second one is the same with n minus 1. And now you have to reinterpret. What you observe now is that each term here, this piece, is actually a periodic function of period p to the k. So what Legendre's theorem is telling you is some kind of Fourier series for the p-adic valuation of n. That's what's really going on. The period is changing, right? And at one point I thought, well, maybe this is sort of like a Fourier series because when you do Fourier series, all the terms have the same period. But they don't, right? When you do Fourier series, you sum sine x of period 2 pi, sine 2x, that has period pi, sine 3x, period pi over 3, so the period is changing. So you do Fourier series, what you're doing is taking each piece, each function has a different period, you combine them in a clever way, and then you put them all together and you get your function that you started with. So this is what's going on here. Okay, here's a homework problem. Do the same thing for these guys. Right, these are some famous numbers, the alternating sign matrix numbers. Right, you all know here what they count. Ascita. I think it's a very interesting homework problem to your number theory class to prove that these numbers are integers without counting. You need to do something. It's not so easy, but it's doable. This is what the picture looks like. This is the picture of the power of 2 that divides this ASM. So now we have more data. I joined the lines because they look better with dots. Sometimes they look ugly. So here's this mountain problem, right? So you stare at this for a while, and then you hope for the best, right? And what would be the best thing that could happen in your problem is that clearly there's a scaling problem, right? These mountains are not the same size. So I should scale them. And what I was hoping for the first time, I was hoping that this guy here, if I draw it in a 0, 1, 0, 1 square, it would be this picture here. And then I'll be done. Not quite. Life is not that simple. Actually, after a while, if you rescale it, you can see that this picture converges to an interesting function, but that's for another day. So when you have data like that, and you want to know a formula for these guys, you observe lots of symmetry, right? Look at these little pieces here, they reappear here. This one here it appears here also, and there too. Once you spend half your life looking at pictures, then you start seeing more things. I won't tell you how long I spent doing these things. Okay, so what do we do? There. Some numbers appear. It's called the Jacob's numbers. It turns out these numbers appeared by looking, we looked, as I told you before, the first thing we looked at was the pieces where the graph is minimal. So the graph is 0. You look at this data, and then you go to Sloan, or you stare for a while, and then there they are. They have a name. So now you know that you're on the right track. When the numbers you find have a name, then you figure that somebody must have thought of it before. And it turns out that this is a theorem. I'll show you a different proof in a minute. That the numbers are odd if and only if n is one of these numbers. They're like Fibonacci, but with a 2 that is there. So 2 is messing up your recurrence. Okay, here's the picture. And now I'll show you a complete description. So the formulas that appear here is a full description of what this graph is doing. So first of all, keep in mind that the places where the function vanishes satisfies second order recurrence. Second order recurrence tells you that you have to look, if you want to know something about a number, you have to look 2 steps back. So somehow, in this picture, it was silly of me to think that this mountain here should be the same as that one scaled. That's not a second order recurrence, it's a first order recurrence. Second order recurrence tells me that I should use both mountains here. This one, that one should play a role somehow. So this is what you can prove. First of all, the piece here, this mountain peak, has as basis these Jacob's numbers. In the middle, this is symmetric, as you can see. In the middle has the highest value. The highest value occurs exactly at the power of 2. Okay? Not only that, but the height is exactly this piece here, this value here. So that height corresponds to this number here. The power of 2 that divides this function at Jn is 0. That's what I just said here. And then the lots of properties, I won't bore you reading what they say, but they say essentially the following. First of all, in this period, the graph is symmetric with respect to this peak. That should be this one here, maybe. Right? The last one, the symmetry. Then, that part up there, the top of the mountain, is exactly this one. And then, the little piece that you need to go to the middle part to start the top, that little piece is that part plus a line. Okay? I won't tell you how long it took us to figure this out. But once we figure what the right formula should be, then the proof should be easy. It is to find these formulas is what takes time, not to prove them. Well, that's an exaggeration, but the ones that I can prove, they don't take too long to prove.
So you find it completely empirically?
Yeah. We draw and stare.
By planning, interactively.
You take the mountain, you move it a little bit and see what happens, and then you rescale and see what happens, and...
No, that's very beautiful, but the next step would be to teach a computer to do the step.
No, why? Then I lose all my fun. No. That you're wrong there. No. No, that's silly.
But there's so many sequences eventually.
Huh?
Eventually you maybe get tired of doing it for many sequences.
No, I don't. Here's what happens for other primes. So for other primes, you get your peaks, you get little peaks, and because the prime is not 2, you get, say this is p equal 5, there are 4 little mountains here trying to compete with the big one, so everything is the same, I think. This is one of my student theses, so I shouldn't say. There's a student that's doing exactly what we did for prime p equal 2, she's finishing all this for any prime. There's no restriction for the prime, the proofs get more complicated, the recurrences get more complicated as you can imagine, but the structure is the same. That's a theorem. This is a theorem that just appeared. So it tells me that the p-adic valuation of the ASM numbers, okay, is again a series, like Legendre's theorem, where each of the components is a function that's periodic of period p to the j. And the formulas are this. These functions look like this. There's your period, there's 0 for a little bit, there's 0 for a little bit, and then they're like this. So these objects are, I'm starting to think that these functions like this, that appear for factorials and for ASM numbers, are what should be the analog of discrete sines and cosines for this type of problems. This should be your basic functions. What we have no idea how to establish, I need some orthogonality. I need to be able to pull out of a function the Fourier coefficients. You cannot do that if you don't know orthogonality. And orthogonality is missing in this theory. We don't know, we have no idea how to introduce orthogonality. The obvious sort of, that the sum of something is 0 doesn't work. The obvious ways of extending orthogonality to this problem doesn't work. It needs a new idea. Okay. The same phenomena should work for this product. The original number has a 3 there, okay? And we have done some preliminary work where more or less all the techniques work, but I think the more interesting question for this product here is what do they count? So this should count n by n matrices with certain restrictions. I thought at one point, so where is a 3 going to come from, right? You have n by n matrices with zeros, ones, and minus ones. So the 3 comes because of these 3 numbers. 0, 1, 1 and minus 1, 0 is obvious, and 1 and minus 1 are the 2 roots of unity. So I thought the q here, it should be q minus 1 roots of unity, and 0 somewhere. But if you put them at random, there are too many. This number is too small for putting the, so there has to be something that replaces the condition that the non-zero entries alternate in the ASM numbers for this. And I don't know what it should be.
So it's obviously an integer because it's only true for, if q equals 2, is it an integer? When q equals 2, is
yeah.
Is an integer, no?
Yeah, yeah. This is obviously an integer, but obviously meaning you can prove it.
Yeah.
Yeah.
No, but then for q equals 2 even? For q equals 3, I know. So
yeah, for any q.
For any q.
For any q, yeah.
For q equals 1? No.
1 is not an integer. Okay.
But then do you know what it counts?
Huh?
For q equals 2, that is...
No, I don't know. I haven't thought of q, no, I haven't thought carefully really about this counting problem. I don't know how to count. These are Stirling numbers. Let's see, I want to show you one, 5:30. When do I have to finish?
5:49.
49, I gotta show you that. I thought it was 48. Good. Okay.
And
Okay. I'll say something about Stirling numbers. I'll mostly show you pictures, okay, because there's nothing I can say. Really. These are Stirling numbers that you know well. Stirling is the second kind. Those are the p-adic valuations. Okay. Some of them look really pretty, like this one, and some of them don't, like this one. I have no idea which is which. This is 196, I know that for sure. This is Sn, 196. I have no idea why is 196 so pretty compared to the other ones. But there's a lot that one can do here, that one should try. But I've run out of ideas for a while, so. Okay. Yeah, let me show you this, and then I'll skip the next part. So what I'm going to show you is a mechanism that out of these pictures we produce a binary tree. So I'm going to take one example. I take example in equal. I think the picture for n equal 5. For k equal 5, sorry. So I draw a root, and this root represents all integers, all positive integers. Okay? And for that root, I ask the following question. Right here, it's closer. So I look at S